Welcome everyone to my course Formal Methods for System Verification. In today's class, we will learn this DPLL algorithm overall. So, we have already discussed various parts of this DPLL algorithm in last two classes. Just to recap, there are primary three things: a decision about a variable. Once you take a decision, you can actually apply this unit clause resolution iteratively, which is called Boolean constant propagation. And if there is no further no conflict and no further BCP is possible, you go back and assign next variable and this process continue. By this way, if you get a full assignment, you get the satisfiability, but if you reach a conflict based of these partial assignments, we do the analyze conflict, right. And this is one of the main part of this DPLL algorithm, and we have already discussed this in detail in last class, in which we talked about that during this conflict, we identify separating cart, and for each cart we will get a conflict clause, but then we will say the asserting clause is the good one, because that will allow you to take the immediate BCP, right. So, and identifying this asserting clause, you need UIP, and we also have discussed that for every decision level decision node, root node, there are multiple UIPs possible, and I will pick the UIP which is closest to the conflict node, and that is efficient. This is the earliest possible time we can reach to this. So, the algorithm will be efficient. This will give a smaller conflict clause, right, and also focusing the center of action, because this is where the conflict happen, and this is efficient to implement. And I will basically explain an algorithm today which I can compute the asserting clause starting from this conflict node going up to the UIP 1. Okay. So, in today's class, effectively what I will show you this overall algorithm and every steps in an algorithmic perspective, right, what I am going to do there. To start with, we have already discussed why this UIP 1 is create a smaller clot. This the repeated example from the last class. So, for this cart, it will take the UIP 1 corresponding to the current decision level and give you the asserting clause, which is not of x 2 or not of x 6 or not of x 1. If you take other carts which take the UIP 2 of the current decision level, you get a bigger clause, which is not of x 2 or not of x 4 or not of x 5 or not of x 1. So, this is has 4 literal, this has 3 literal. So, I am going to pick this one. Now, the question is how do you compute this clause? When I get the conflict, how do I compute this clause automatically or algorithmically, right? So, I am saying that this can be done with binary clause resolution starting from this conflict node. So, just to recap what was the binary clause resolution, you have two clauses C1 and C2 in which have other literals B1 to A1 to AN and B1 to BM, but specifically you have one literal beta here and not of beta here. And binary clause resolution says that you can combine these to a new clause C3 where I can remove this beta and not beta, because they will eventually not impact the final decision, that I have already discussed in previous class. And I will construct a new clause which is combination of the other literal A1 to AN and B1 to BM, okay. And I will remove this C1 and C2 altogether, right. This is the binary resolution. So, what I am saying that once I get a conflict, I will from that node I will start this binary resolution automatically until this UIP 1, and whatever the clause I get, that is my asserting clause, right. Let us see what is happening. So, let us take as a minimal example now. So, let us I have these 4 clauses which result into this conflict. So, let me write down these clauses C1, which is not x 4, x 2 and x 3, not of x 4 or x 2 or x 3. C2 is not of x 4, x 10, x 6. C2 is not of x 4 or x 10 or x 6, and C3 is not of x 5, not of x 6, not of x 7, not of x 5, not of x 6, not of x 7, and C4 is not of x 7, not of x 6, not x 7, right, not of x6 or x7. So, these are the 4 clauses, and if you take decision, you will get this conflict. So, let me just show how this things is happening. Let us say I have also other clauses, other variables, right. So, which I am not taking here because I just want to discuss this conflict. Okay. So, suppose you have taken a decision x2, you have something else is happening earlier, right. So, I am not constructing the entire graph, I am just constructing the part which I need here. Let us say I have taken x2 equal to false at decision level 3, and also I have taken x4 at decision level 5 and x10 is equal to false at decision level 4. So, these are the decision happen, right, by this way. If you now take C1, x2 equal to false, so this will make this is false, x4 equal to true, so this will make this false. So, this force me to take x5 equal to 1, right. So, yeah, C1 is x4, x2, x3. So, this is x5. So, this is actually x5. So, if I take this this particular decision and this decision and I consider C1, x not of x2 make this is false, not of x4 makes this is false, and then not of x2 will this is x2. So, this will make this false. So, x5 equal to 1, right. So, this will make this true. Similarly, if you consider C2, here you have x4 equal to true. So, this will make this false, x10 equal to false. So, this will make this false. So, x6 equal to 1 to make this true, right. Now, from C3, if I put x5 equal to true, so this will become this false, x6 equal to true, so this will make this false, which say that not of x7 should be true here, or x7 so is basically false, right. And from C4, now you have x7 equal to false, so this will make this is false, and x6 equal to true, so this will make this false. So, I get a conflict at decision level 5. Okay. So, this conflict I get. Now, we have already discussed what is UIP and all. So, for decision level 5, what are the UIP? This is UIP definitely. This is the only UIP, right, because there are 3 other nodes, they are not UIP because there are other paths which is not. If you consider this one, there are path through this which is not coming from this, and similarly if you consider this and this, there are path through this which is not coming through this. So, they are not UIP. So, for decision level 5, there is only one UIP. Okay. Now, you have to consider a cut which consider this, and this is one of the cut, right. So, what I am saying, I am not going to consider the cut. I know that this is the UIP, I calculate what are the UIP, and I found out this is the UIP. I will start from this node and I will do the binary clause resolution, and I will reach to this node, and then it will give me the separating cut. What is the clause corresponding to, by the way? It is basically x2 or not of x4 or x10. This is the asserting clause I want to construct, but this cut is something visual is fine, right, but I want to do it algorithmically. So, I will start from this node and I apply basically this algorithm. Before going to this algorithm, I will basically explain what is happening here. So, I have the conflict here coming from C4, right. So, this is coming because of say not x7, right. So, it is coming because of not x7. So, the variable here is effectively 7 x7, right, and its antecedent is C3 because it is coming from C3. So, what I will do now, I will basically do binary clause resolution between C3 and C4. Okay. So, what is your C3? This is your C3, this is your C4, and what is against which variable? This variable. So, you see here it is x7 here and here not x7, right. So, if I combine, it will combine this part and this part, and not x6 is common. So, I will get this is the new clause I learned, right. So, this is effectively I do it. So, I get C5. Now, here I will pick say variable is say x6, okay. Literature is not x6 and variable is x6, and then this x6 is coming because of C2, right, because this is the antecedent of this C2. So, now I will combine C5 and C2. So, basically what I do, I initially take C4, I will get the variable x7, antecedent is C3. So, then C4 and C3 I combine, I got C5. Now, I will basically go through this, right, or I will go through this, I got x6 which is my variable and antecedent is C2. Now, I combine C5 and C2, right. So, what is happening here? I have C5 and this is my C2, my variable is x6, right. So, I have not x6 here, x6 here. If I combine, I will get this plus this, right, which is not of x4, not of x5 and x10. So, this is my new clause I learned. Okay. Now, I got C6 and now I will go back here. So, now this is coming from this. So, now if I consider x5, I have antecedent is C1, right. So, now I combine C1 with C6, I combine with C1 with C6 and my variable is x5 and literal is not x6. So, now x not x5 and x5, right, in C6 and C1, and then if I combine, it will give me this plus this, which is x2 not x4 and x10. So, this is the clause I will get, and now it consists of my UIP node, right. So, I have this not of x4 here. So, I will stop here, and you see this is the this is corresponding to this cut, right, x2 not x4 x10, x2 not x4 x10, right. So, this is what I am going to do effectively, right. So, I start from this node, I keep identifying. So, this is the algorithm effectively, right. So, this is my current conflict node, current clause. Then stopping criteria is that I reach the UIP 1, right. Then I will identify what is the last assigned literal, which is basically x7, right. So, I will basically I get not of x7 and the variable is basically x7, and then I will identify the antecedent of this variable, which is in this case C3. So, I got C3 and the actual current clause C4. So, I will do this binary resolution, I will get the new clause C5, right. And then I go back, I see whether in the new clause I have the UIP 1, it is not. Again I will take a literal, last assigned literal. So, which is basically C6 x6, and then I will identify the antecedent C2, then C5 and C2 I will do the resolution, I will get C6. Again I will identify what is the last assigned one, this one, and from the antecedent is C1, then I will do C1 and C6, I will get C7, which is my final clause, which will has this x4. So, I will stop there. So, my stopping criteria met. So, this is the analyze conflict algorithm, right. So, which basically does not compute the separating cut anything, it identify the UIPs, and then in iteration it will just do this, and then it construct the asserting clause, right, and then add this clause to the formula, and then what is the second highest DL in this particular clause, whatever the clause I got, there I stop, right. So, in my case, so I basically got the conflict in decision level 5. So, I will remove everything of 5, I will keep up to 4, right. So, this node I will keep, this part of the graph I will remove, right. So, I will and then I will restart the process again. Okay. So, this is efficient algorithm to compute the conflict clause, which is asserting. Okay. So, now this is the overall DPLL algorithm, let us give you. So, initially there may be some unit clause in your actual formula. So, I will apply BCP, and if I get a conflict, that means initially the formula itself is unset, I will stop there, because if you keep applying BCP and if you get unset, that means a conflict means the assignment reached to a conflicting situation. So, that initial formula without any assumption, automatic propagation itself reaching to a conflict, right. So, the formula will be unset. Otherwise, I will just take a decision about a variable, and this decide what it does, it basically choose an unassigned variable and assign a truth value to it, right. So, we will talk about what is a good way of doing that and in the next class. Let us say I pick some variable and some truth value. If there is no further variable remain, then this is false, it will return false. That means all variables are already assigned. So, if it is not of decide, that means sat, that means all variables are already assigned. So, I get a satisfiability. Otherwise, we will do the BCP, and if BCP reach conflict, I will call this analyze conflict function that I have already discussed, and if the backtracking level that it returns is less than 0, right, then I will basically say unset. Okay. This is again can only happen if you got in decision 0 itself you got some conflict. Okay. Otherwise, you do the backtrack and you go back and you again take a decision and do this, right. So, this is effectively this loop, right, this algorithm in detail. Okay. So, we understood decide, that take a decision, but again this is it is not random in a set solver, which variable to choose and what value to be chose, right. So, this is something, some heuristics are there, but logically what you will do effectively, you try to pick the variable that occurs in maximum clauses, so that this value will impact many clauses, right. So, I will try to identify a literal that occurs in many clauses, right. Also we will see that smaller clause is easy to decide, right. If there are two literal, if I know the one value, I can decide about the other variable. So, the smaller clause are better. So, we will try to see the literal that occurs in smaller clauses and more frequently, right. And based on whether it occurs as a x or not x, I can decide the value whether it is a true or false, right. So, this is the in high level, but we will talk about many heuristic on that. BCP I have already discussed that this is just unit clause propagation. So, it may return conflict if a conflict encounters, otherwise just apply this unit clause resolution, right, until I reach a conflict or there is no more implication possible, right. And then it is also apply in line 2, because at the start itself you may have some unary clause. And backtrack is I already discussed that it is, if the current level decision level is this, it just erase all the nodes in the current decision level and go to the DL minus 1. Okay. So, this is the overall DPLL algorithm in a nutshell. So, one thing we have to first understand the correctness and termination of this DPLL. Is it the algorithm that it will continue, because you see here I have a infinite loop, right, while true. Is it that this will keep continuing to do that? Or it will terminate, right, that is the first questions, and we are adding these clauses, so into the original clause. So, does it consistent with the original clause? So, that we should understand, right. So, the first question is that the new clause that I learned is consistent with the existing clauses, and the answer is obviously yes, because how do I construct this conflict clause? By using binary clause resolution. So, it is kind of a consequence of the current clauses, right. So, whatever I show here, it is basically I learned this clause by from C1 and C6, C6 I learned from C2 and C5, C5 I learned from C4 and C3. So, effectively this C6 is a consequent of these clauses. So, this must be consistent with my existing clauses. Okay. Next question is that how do I show that this DPLL always terminate, right, because you are running an infinite loop. So, it can be shown that if we have say if you have a conflict happen in decision level DL plus 1, right, and I go back to DL minus 1. So, you basically have a conflict here at DL plus 1 some level, so this is 5, right, and I backtrack to say some DL minus 1 minus, right. So, this may be say 3 if 4 does not occur here, right. Then what I am saying that, and I learned some new clauses, right, that is the new clause I learned. So, this ensures that this if algorithm reaches DL plus 1 from DL minus 1 and at a conflict here, it will never traverse this path, because I learned some clauses, right. So, the new asserting clause that I learned makes sure that if the algorithm never reaches this DL plus 1 from DL minus 1 with the same partial assignment, that means this path. So, eventually if you have n variable, there are n 2 to the power n possible combinations, and every time you are excluding one possible combinations, right. So, effectively there are 2 to the power n possibilities, and eventually you are excluding one by one, and you will never come back, and so that means you will exclude all of the possibilities eventually, right. Hence, this algorithm always terminate. Okay. So, there is one more interesting thing we should understand here, which is the called clause learning. What is happening here? So, every time I take some decision, I got a conflict, I learned something, right. So, make sure that I do not come back to the same path. But now, let us take this situation. Let us say you have taken x equal to 1 at decision level, say this is 1, right. So, this is a decision level 1, 2, 3, 4, 5, 6, 7, 8, 9. So, you have taken decision level 2 x equal to 1, and this means BCP. After that, there are some BCP happen. Then again you take another variable, say x some y equal to something. So, you go to the next level. Whenever you take a new decision, you go to the next level, and again some BCP happen, you take another decision, again BCP happen, again you take a decision, and again BCP happen, again you take a decision, right, again you take BCP, you take a decision, and so on, and then finally you get a conflict. Okay. And then whenever conflict happen, you go back to the some previous level, right. Again you have BCP because this is asserting clause, again some conflict happen, you go back to the previous level, again BCP happen, you take some decision, you take some decision, BCP happen, you take some decision, BCP happen, take some decision, and so on, right, and finally you get a conflict, you go back to the previous level, again some conflict happen, you go back to previous level, you take some decision. So, this is how the SAT solver will do on, right. So, either BCP, conflict, go back previous one and go back, right, and this will happen, and finally let us say you have a conflict and you go back to this. What effectively it says that the initial decision x equal to 1 is wrong, right. You go back to the decision level 1 now, and you basically took x equal to 0, because x equal to 1 is the problem. So, if your initial decision is wrong, all these things you are doing here looks waste of time, right, because finally all this decision BCP what you have done all are wrong, because your first decision itself was wrong. So, is it something that is a waste of work? Most of the cases the answer is no, because whatever we are doing here, we are learning something, right. Each conflict clause, each conflict will give me a conflict clause or a new clause, right. Each of these conflict is giving me something that this should not happen here. Now, whenever x equal to 0, and if you do this process, I make sure that those assignments will not happen here, right. So, whatever the decision learning is happening here, they will not repeat here. As a result, whatever the clause learning is happening, even if your initial decision was wrong, they are not waste of work, they are actually useful in subsequent passes. Okay. So, this is something, that is why this DPLL algorithm is so popular and so powerful. So, to conclude this class, we have many SAT solver, and these are widely used in industry, in academic, many as research domain, whether you think about hardware verification, it can be scheduling, it can be cryptography analysis, everywhere people try to model their problem into a SAT problem and try to solve them. And if you are really interested, you should look into the SAT solver like Minisat, Glucose, Cadical, Z3, Crypto Minisat, KeySat, MapleSat. So, these are very popular SAT solver and they are very powerful, right. So, I hope you will use some of them in your research and studies. Okay. With this I conclude this class. Thank you.